Okay, so let's move on. In the last class, we have discussed a number of more complex crystal structures. And I would like to add one more before we over to the next chapter. So the next crystal structure I would like to discuss is the Spinel structure. So the Spinel structure has the composition AD2O4. Okay, so you see that this is a ternary compound, and in the Spinel structure, we will have 1/8 of the tetrahedral holes filled, a half of the octahedral holes filled, and the oxygens, they make the cubic close packed structure. So the parent compound of the Spinel structure is the magnesium aluminum 2O4. So in this case, we would have magnesium in 1/8 of the tetrahedral holes, the aluminum in half of the octahedral holes, and the oxygen atom would make the cubic closed packed structure. So now, of course, there's the question, when we have only 1/8 of the tetrahedral holes being filled, then which of these tetrahedral holes are being filled? And as only half of the octahedral holes are being filled, which octahedral holes are being filled? Okay, so this filling occurs now in a relatively complicated pattern. We have actually a cubic unit cell that contains overall 32 oxide ions. Okay, so one unit cell has actually the composition AB2048. So there are 8 formula units in the unit cell due to the relatively complex hole filling. So you see the overall unit cell here, but it looks complicated. So let's try to systematically understand the structure of the spinel. So you can most easily understand it when you put the tetrahedral holes, or you place the tetrahedral holes so that they occupy the corners and the face centers of the unit cell. Okay, you can do this by just shifting the coordinate system. Okay, so in the regular cubic closed packed structure, of course, the oxide ions would sit on the corner of the unit cell, but as we have seen a number of times before, it is possible to basically translate along a vector so that now in this case, the tetrahedral holes sit on the corners and the face centers of the unit cell. Okay, so now you see, so now we can actually segregate this big unit cell into 8 subcells. Okay, so now this big cube overall will contain 8 of these smaller cubic subcells. Okay, you see one here, there's another one here, there's a third one here, and there would be 5 others. So the fourth one would be this one here, okay, and then there would be 4 other ones in the back of the large unit cell. So each of these smaller subcells, they contain cubes denoted here and here respectively, and overall we have 2 different types of cubes. Okay, and one type of cube, this one here, is centered. Okay, in the center of that cube we have, well, an A atom. Okay, in this case that would be a magnesium atom. Okay, now only 50% of the corners of this red cube here will be occupied, and they will be occupied by oxygen atoms. Okay, so that the oxygen atoms surround the A atoms tetrahedrally. That has to be so because these centers also formally represent tetrahedral holes. So now, in addition to this cube, we have this type of cube. So this cube is not centered, but all corners are being occupied. You see that half of the corners are occupied by oxygen, and half of the corners are occupied by aluminum atoms. Okay? So the aluminum atoms, they are, well, formerly in the tetrahedral holes. You can see this actually by the fact that when you, well, add more than one of these unit cells together, then each of these aluminums will be surrounded by 8 oxygens. So this would be the first one, this would be the second one, this would be the third one. So the fourth one would be here if you extend this edge. So the fifth one would be here when you extend this edge. Okay, and the sixth one would be here when you extend this edge here. Okay, and now the oxygens are surrounded also by 8 aluminums, and that has to be so because, as you've learned in a cubic unit cell, the octahedral hole and the spheres are commutative. All right. So now you see that here in the front of this big cube we have, well, 2 of these kinds of cubes and 2 of these kinds of cubes. So they kind of alternate here in the front, and the same would be here in the back, not shown. Okay, so there would be 4 other of these red cubes also in the back of this big unit cell. Okay, so then our unit cell would be complete. Okay, so this is probably the most straightforward way to understand this relatively complex Spinel structure. Okay, so now in addition to regular spinels, we have also something which is called the inverse spinel. Okay, and in the inverse spinel, we would have our B atoms on the tetrahedral holes. Okay, so now our B atoms have actually a higher preference for the tetrahedral holes than to the octahedral holes. Okay, therefore they actually displace the A atoms from the tetrahedral holes. From the tetrahedral holes, and the A atoms have to occupy the octahedral holes. Okay, but now because we have relatively few A atoms available, and too many of the B atoms to fill 1/8 of the tetrahedral holes, the remaining B atoms occupy the octahedral holes. Okay, so this is realized, for instance, in compounds like magnesium, gallium-2O4, or Fe3O4. So in this case, we would have a mixed valence compound of iron-2 and iron-3. Okay, and in this case, well, the iron-3 would occupy all the tetrahedral holes, okay, available in the Spinel structure, and the remaining one would go in the octahedral holes, and, well, all the A atoms, that would be iron-2 plus, would occupy the remaining octahedral holes. Okay, so such an inverse Spinel structure you have when the B atoms have a particular affinity for the tetrahedral holes. Now, oftentimes, however, A and B have similar affinities. Okay, and then you get what is called the mixed spinels. In the most extreme case, the affinities are, well, the same, and there's a statistical distribution over the atoms A and B over the tetrahedral holes and the octahedral holes, respectively. Okay. Now, of course, we have to have 2 times as many B atoms than A atoms, so that would require that the ratio of A to B in the tetrahedral holes is 1 to 2, and in the octahedral holes that's the same. So you see here the ratio of A to B is 2/3 to 4/3, that's also 1 to 2. Of course, overall, we have to have twice as many octahedral holes filled rather than tetrahedral holes filled. Okay, so now, in other words, when the degree of inversion is actually 2/3, okay, then that means that there's a statistical distribution of A and B over the tetrahedral holes and octahedral holes, respectively. All right, so this is the Spinel structure and the inverse Spinel structure, as well as the mixed Spinel structure, which will be our last more complex structure that I wanted to discuss. Of course, there are many more crystal structures, but the discussed ones can be considered to be the most important ones, the ones that actually occur most frequently in nature. Okay, so now let us go to the next chapter. And the next chapter will now be about bonding in extended solids. So now we know 3 different basic kinds of bonding. Well, that's the ionic bonding, that's the covalent bonding, and the metallic bonding. And we will find all 3 bonding types in extended solids. So now the following, I would like to go step by step through the bonding types. We will discuss the bonding theories that can explain these bonding types in, well, extended solids. All right, now when we look at the elements, okay, then many of the elements are solids, so most of them are actually solids. So all the metals, with the exception of the mercury and, well, the cesium and perhaps also the gallium. So gallium is a borderline case. They are solids. Okay, so then we have the metalloids. These are these elements here. They're also all solids at room temperature. Only the non-metals, like nitrogen, oxygen, fluorine, for instance, they are not solids, even though some of them, like the sulfur or the iodine, they are still solids. All right. So it is possible to explain bonding types using the concept of electronegativity. Okay, so electronegativity is the ability of the atoms within the compound to attract electrons within the chemical bond. So with the concept of electronegativity in electronegativity differences, we will see that we can explain all these 3 bonding types pretty well. Now let us first look at the elements. Okay, so you see here again the periodic table with the elements, and you see the respective electronegativity value associated with them. So we first have to remember that in the periodic table, the electronegativity increases from the left to the right within a period. Okay, and the electronegativity decreases down a group, and that holds true pretty much for all groups. Okay, so that makes the cesium the most electropositive element. There's a electronegativity of 0.8. We won't discuss francium here because it's radioactive. And the fluorine is the most electronegative element. Okay. So now let us see if we can correlate the bonding types with the electronegativity. Okay. So now these elements here, they are all metals with metallic bonding in between them. So we see that with few exceptions, they all have pretty low electronegativities. Okay, they're typically below 2. There are few exceptions, like gold, for instance, has an electronegativity higher than 2, platinum, iridium. So typically very noble elements tend to have unusually high electronegativities, but if we take out these few exceptions, then we can say that the electronegativities within metals are generally on the smaller side, typically lower than 2. Okay. Now, how can we understand this? Well, we can understand this when we consider that in metallic bonding, the electrons are being equally shared between the metal atoms, okay? Because there's no, well, electronegativity difference between the metal atoms. Okay, so therefore they like to share the electrons, but on the other hand, they also don't have a particularly high affinity to these electrons. Okay, so therefore they're actually delocalized. Okay, so metallic bonding can be considered as a form of nonpolar bonding, where the bonding electrons are being delocalized. Okay, so that gives rise to the character of the metallic bonding. Okay, so now on the other hand, in a non-metal, the electronegativity difference between the atoms is also 0. So for instance, in fluorine, well, all the fluorine atoms will attract the electrons equally strongly. Okay, but now in contrast to the metals, the fluorine atoms all have a high affinity to these valence electrons, and that leads to the localization of the bonding electrons in between the atoms. Okay, and that leads to the formation of a covalent bond. Okay, for the metalloids, we have kind of have a case in between. Okay, so metalloids, they have typically electronegativity of around 2. Okay, can be a little bit lower or a little higher. Okay, and then the non-metals, they have typically electronegativity significantly higher than 2. All right, so using that concept, we can already explain the bonding types in elements. So now let us look at compounds made of 2 different elements. So in these compounds, the electronegativity difference between the atoms will never be exactly 0. Okay, it will be always larger than 0. So therefore, the bonding in the respective compounds has to be at least to some extent polar. Okay, so now the degree of the polarity will depend on the electronegativity difference. Okay, so now which degree of ionic character a compound has can be nicely described using the concept of the catalyzed triangle. So in catalyzed triangle, we have 2 axes. So this is the y-axis, the y-axis, in which the electronegativity difference between the atoms is plotted. And here on the x-axis, we have the average electronegativity of the atoms involved. Okay? So now all, well, substances here on this x-axis, where delta En is equal to 0, constitute the elements. Okay? Because only in elements we have an electronegativity difference of 0. Okay? So now here at this end, we would find, well, the cesium. Okay, the electronegativity difference in cesium metal is 0, and the average electronegativity of, well, cesium within cesium metal is just, well, the electronegativity of cesium metal. Okay, and now here at the other end, we will have the fluorine. So within fluorine, the electronegativity difference is also 0. Okay, but the average electronegativity difference of the fluorine atoms, well, that's just the electronegativity of a single fluorine atom, which is equal to 4.0. All right. So now, what is the compound with the highest electronegativity difference? Well, then that must be then the cesium fluoride. Okay, so the cesium fluoride would be about here. It has an, well, intermediate average electronegativity difference because the electronegativity of cesium is very low and the electronegativity of the fluorine is very high. But the electronegativity difference is maximized. Okay, so this represents this point here. And if you connect now all these 3 points, then that gives a triangle. Okay, so now all possible compounds, okay, they must actually lie within that triangle. And the closer they are located to this corner, the more ionic their character. The more they are located toward this corner here for the cesium, the more metallic their character. And the more they are located toward this corner here, the more covalent. Okay, so you see, for instance, magnesium oxide lies here. So in a very simplistic view, would say, well, magnesium oxide, that's an ionic compound. Okay, but it's actually not precisely true. It's mostly an ionic compound. But if it was entirely an ionic compound, the electronegativity difference would actually be infinite. And of course, that cannot be. Electronegativity always has to be finite. Okay, for that reason, well, our magnesium oxide has to lie within that triangle at a certain distance from this corner and this corner as well. So you would expect that there are also certain metallic and covalent contributions, even though these covalent contributions may be fairly small. Okay, so when we look at, for instance, P2O5, okay, then we are already more toward covalent, okay, but we are certainly not entirely covalent because we are not really on this corner here. We still have a distance from this corner here, and we have also finite distance from that corner. That means that also, well, some metallic contributions can be in some degree of electron delocalization can be assumed. Okay, so last example, when we have a compound like copper, aluminum 2, then this compound would sit here. Okay, of course, now we are much more here at the metallic end. So overall, we would characterize this compound to be metallic, but because of electronegativity difference between copper and aluminum, we would also find some ionic contributions, okay, but also some covalent contributions to the bonding. All right. Now let us look at bonding theories that can explain these three types of bonding: ionic, covalent, and metallic. So let us look first at the ionic theories for ionic bonding theory, keeping in mind that 100% ionicity can never be achieved for the reasons we just discussed, because 100% ionicity would mean infinite electronegativity difference, which is practically not possible. All right, so we would regard sodium chloride as a typical example of an extended solid that makes ionic bonding. How can we explain the ionic bonding in sodium chloride? Okay, so we would assume that when a sodium atom reacts with a chlorine atom, that an electron is being transferred from the sodium atom to the chlorine atom, making the sodium a sodium plus and the chlorine a chloride minus. However, when you look at the ionization energy of sodium, we'll find it's 3.14 electron volts. And when you look at the electron affinity of chlorine, then it's 3.61 electron volts. All right. So now, basically, that would say that it takes more energy to remove the electron from the sodium than we can actually gain energy by adding that removed electron from the chlorine. Okay. So now you have to keep in mind, and that would mean that sodium chloride should actually be unstable. Okay, but it's very stable. So how can we explain this? We can explain this by the fact that ionization energies and electron affinities apply to atoms in the gas phase. So indeed, if we had sodium in the gas phase and chlorine atoms in the gas phase, we would not expect a reaction between the sodium and the chlorine for exactly that reason. That would actually imply that sodium chloride vapor also is unstable. Okay, in the gas phase, indeed, the chlorine would actually move its, or the chloride would actually move its electron to the sodium. Okay, and you'd have a vapor mixture of sodium vapor and chlorine gas. Okay, so now if there's such a great instability in the gas phase, why is sodium chloride perfectly stable in the solid state? Okay, now that is because of what is called the lattice enthalpy or the lattice energy. Okay, if we bring the sodium ion and the chloride ion from the gas phase where they have a large distance together, okay, to form a crystal, then we can effectively harness on the electrostatic attractions between the cations and the anions. Okay, so that reactions M plus gas plus X minus gas gives MX solid is energetically highly favorable because of the electrostatic attractions between the cation and the anion. Okay, so the lattice energy is an enthalpy. It does not actually consider entropy, which would also contribute to the overall free energy, which would give you the overall driving force for the reaction. But typically, when we form extended solids and have reactions between extended solids, the entropy considerations can be neglected. Okay, so what we would expect is that the well, reaction or the driving force for reaction is dominated by the lattice energy, and that we would expect the crystal structure, okay, that has the highest associated, that gives you the highest lattice energy. Okay, so how can we systematically approach the concept of lattice energy and actually calculate lattice energy based on the electrostatic interactions between the ions? All right. So you can do this in a fairly straightforward way. So here we calculate the lattice energy of a binary compound A, B, whereby A is the cation and B is the anion. Okay. Then the term for the Coulomb interactions between, well, a pair of a cation and an anion is given by this term here, because it's the Coulomb potential for an ion pair. It's just the charge of the cation times the charge of the anion times the elementary charge square over 4 pi times the dielectric constant of the vacuum times the shortest distance, RAB, between the cation and the anion. Okay? So now in the crystal, we should say, right? So now in the crystal we have many ion pairs. Okay, so a crystal is being made of many, many atoms. So we can multiply this by, well, the Avogadro constant n when we want to consider 1 mole of well, ion pairs. Okay, so now this term then is multiplied with what is called the Madelung constant, which will now account for the different structure types and account for the fact that in different structure types, well, ions are surrounded differently in a different way by the remaining ions. Okay, so overall the lattice energy is minus, and the minus sign is because of the exothermic nature of the crystal formation from the gas phase, times the Madelung constant, which depends on the structure type, times C plus times C minus times the elementary charge square over 4 pi epsilon 0 RAB times N. All right, so now this is still over simplistic because we neglect the fact that there are also repulsions between oppositely charged ions. If that wasn't so, then the distance between a cation and an anion in a crystal would be infinitely small. Okay, but there is an equilibrium distance between the cation and the anion. That is because there are also repulsive interactions. Okay, and the repulsive interactions are due to the fact that, well, each ion, whether it's a cation or an anion, contains a nucleus which is always positively charged, and these nuclei repel each other, and that the electron clouds between the cations and the anions also repel each other. Okay, so therefore you have an equilibrium distance. So before we go into that, I would like to briefly talk about how we can calculate the Madelung constant, which we previously just discussed. So the Madelung constant will be dependent on the crystal structure. So here's an example. Here we have the sodium chloride crystal structure. You see the chloride ions, they make the lattice. Okay, so the corners of the unit cell are occupied. The face centers of the unit cell are occupied. And the sodium plus ions, they sit in the octahedral holes. That's the edge centers, as well as the body center. All right. So now, in our approach to the Madelung constant, we, consider now by how many atoms, or sorry, by how many ions a particular ion is surrounded, and what's the distance between the ions, okay, relative to, well, RAB, okay, the closest possible distance between the two ions. So now let's put ourselves on this sodium plus here in the center of the unit cell and consider what are the nearest neighbors, or the nearest neighbors. So the nearest neighbors are these 6 chloride ions, okay? So therefore, a factor of 6 contributed to the Madelung constant for these interactions, okay? So next, let us consider the next nearest neighbors. So the next nearest neighbors relative to this sodium plus are these sodium plus ions that sit on the edge centers of the unit cell. So you see that's overall 12. So that's these 4, that's these 4, and that's these 4. So these surround the central one in a cube octahedral fashion. Okay, so we have 12, but now these 12 cations are further away from our central ion in comparison to the chlorides, okay? And they are by a factor of the square root of 2 farther away, okay? So that is because the distance between this cation here and an anion in the first coordination sphere, well, that's half of the edge length of the unit cell. And you see that the distance between this cation and the nearest cation is this, okay, which is the square root of 2 times this distance here. So this distance here, which is actually half of a face diagonal of the unit cell, okay, is the square root of 2 times longer than this distance. We can calculate this very easily. All right. So therefore, we have to divide 12 by the square root of 2. So we have to place a minus sign here because the interactions between ions of the same charge are negative, okay? So now I can next consider the interaction between this cation and the next nearest neighbors. So the next nearest neighbors would be, well, these chloride ions that sit on the corners of the unit cell. So that's overall 8, okay? But these 8 chloride ions now sit by a factor of the square root of 3 times farther away in comparison to those that sit on the face centers and which are our nearest neighbors. All right. Therefore, now I have to divide this number 8 by the square root of 3. Okay. So now I can continue that. Okay. I consider now the next nearest neighbors, and then the next nearest neighbors, and so forth, and sum all these well, contributions up, and then you will get a number that converges, in the case of the sodium chloride structure, to the value of 1.748. Okay. Now I can do the same for instance, the sodium chloride structure, the zinc sulfide structure, Wurtzite, and the zinc sulfide structure, sphalerite, or zinc blend. And you will see that this gives similar numbers. Okay. However, they are not exactly identical. So when you analyze these numbers, you will see that the coordination number has some influence here. So in the cesium chloride, we have the highest coordination numbers. So each cesium is surrounded by 6 chlorines, and 6 chlorines are surrounded by, each cesium is surrounded by 8 chlorines, and each chlorine is surrounded by 8 cesiums. So we have an 8-8 coordination number here. For sodium chloride, we have a 6-6 coordination, giving slightly smaller numbers. And for both the Wurtzite and the zinc sulfide structure, which have very, very similar values, we have a 4-4 coordination. Okay. If you looked at a single ion pair, well, then of course the coordination number would be 1, and that would give a hypothetical Madelung constant of 1, but that's hypothetical only. You see here that the coordination numbers are slightly correlated with the Madelung constant, but overall the numbers are not very different. All right, but now let's go to the repulsive interactions, which are called the Born repulsion. And the Born repulsion results, as I mentioned previously, from repulsive interactions between the electron clouds and repulsive interactions between the nuclear charges of cations and anions, respectively. So that repulsive factor has to be added to the attractive factor. So you see this here graphically. So here you see the amount of repulsion as a function of the distance of the ions. We see, of course, that when the distance is extremely small, there's very strong repulsion, and as the distance increases, the repulsion approaches 0. So now for the attraction, we see here this is represented by this green curve here. And then the addition of attraction and repulsion gives now the blue curve. Okay, and you see that the blue curve now has a minimum, and the minimum represents the equilibrium distance between the cation and the anion within the crystal structure. Okay, so now overall, the Born repulsion can be described by this term. It's equal to a constant B over the distance to the power of n. So n can vary a bit, but it's typically around 8. The exact value depends on the compressibility of the solid. Okay. So the more compressible a solid is, actually, the more easily you can actually bring atoms together, and that determines, well, this number in the exponent here. But it's typically around 8, which is typically around 8. So now, for the calculation of the overall lattice energy, we now need to consider both the attractive and the repulsive interactions. Okay, so the term for the attractive interactions is this one here. We saw it before. Okay. It's the Avogadro constant times the Madelung constant times the charge at the ions times E squared over 4 pi epsilon 0 r. now plus the Born repulsions, which are expressed by this term B over R to the power of n. So now the lattice energy needs to be, well, maximized. So therefore we need to look for, well, the minimum of du over, well, the minimum for this term here. So the energy is minimum when du over dr is equal to 0. So we therefore have to form the first derivative of this term, u. Okay, and when you calculate the first derivative from this term, then you arrive here at this term, which has to be 0. Okay, and now you can actually solve this equation here for B. And then you have an explicit term for B, which is A times C plus times C minus, charge of the cation times the charge of the anion, times E squared times R to the power of n minus 1 over 4 pi epsilon 0 n. Okay, so now you can actually take this term here for B and plug it into this equation here. So you place B by this term, and then you arrive at the final formula for the lattice energy, which is also called the Born-Lande equation. And it says that the lattice energy is equal to A times n times C plus times C minus E squared over 4 pi epsilon 0 R, sorry, 4 pi epsilon 0 R 0, although R in equilibrium, times 1 minus 1 over the power of n. So when you analyze that, you see that there are a lot of constants. Okay, so E squared is constant, 4 is a constant, pi is a constant, epsilon 0 is a constant. So you will calculate, well, the explicit value from these constants. You arrive at this formula here, which is 1.389 times 10 to the power of 5 times the Madelung constant, which is still here and which depends on the lattice type, times C plus times C minus over R0 times 1 minus 1 over n. Okay, so now we can simplify this equation a little bit further. This equation is still a little bit unhandy because the Madelung constant appears, and the Madelung constant depends on the crystal structure, which we may not always know. However, Kapustinskii found that there is a correlation between the Madelung constant and the number of the ions in the formula unit, and that when you divide the Madelung constant by the number of ions in the formula unit, you get very similar values. Okay, which you can approximate to be a constant. Okay, so now he found that for cesium chloride, well, we would have 1.763 times the number of ions in the formula unit. That would be 2 to give 0.88. For sodium chloride, we would get something very similar because the Madelung constant is already very similar. Now for ionic compounds with more than 2 ions in the formula unit, we get much larger value. But if we divide these values by the number of ions in the formula unit, then that again becomes a very similar value. And the same if you, for instance, look at alpha alumina, which has 5 ions per formula unit. If we divide the Madelung constant by 5, then we again arrive at a value of about 0.8. You see, however, that the exact value depends again on a little bit on the coordination. So in the cesium chloride, we have an 8-8 coordination. In the sodium chloride, it's 6-6. In calcium fluoride, it's 8-4. And in aluminum oxide, it's 6-4. So you see again that there is some weak trend that says that as we actually go to, well, lower coordination numbers, then our, well, values tend to decline a bit, but only a little bit. Okay. Now we can just take an average of these values, okay, and replace the Madelung constant in the Born-Lande equation by the number of formula units. Okay. And that's, of course, much more convenient because we always know the number of formula units, while we may not always know in which crystal structure our substance crystallizes. And then we arrive at a simpler equation, which is now 1.079 times 10 to the power of 5 times the number of formula units times the charge of the ions over, well, the distance between the ions. And that is named after Kapustinskii, the Kapustinskii equation. All right, we are now at the end of this class already. So let's stop the recording.